So this is lecture 27 and 28 to follow at 5 p.m. What were we doing yesterday? Let's have a quick recap. Yesterday I was trying to find the inertia matrix of a cuboid shown here at its center of mass, denoted by C here, and relative to the coordinate system mentioned here. Keep in mind that whenever we talk about an inertia matrix, there are three things you should specify. The inertia matrix is of an RB, of a body, about a point, and relative to a given Cartesian coordinate system. Right? So IC matrix, what I am writing here, it is of an RB, which is the cuboid, shown cuboid, at its center of mass and relative to the coordinate system that I have shown. Indeed, I performed the full integration to arrive at these three diagonal components, where M is the total mass of the RB, and A, B and C are the different edge lengths. A is the length of that edge, or rather those edges, 4 of them, which are parallel to E1. B is the length of the 4 edges which are parallel to E2, and C is the length of those 4 edges of the cuboid which are parallel to E3. These are the diagonal elements we get from full integration. For the off diagonal elements of this matrix, mind you, I really did not perform any integration. I did not have to perform any integration. Why? I realized in the very beginning that if I have to find the off diagonal components of the inertia matrix of this RB at point C relative to the coordinate system shown here, I realized very early that the plane of x1 E1 and x3 E3 is a plane of symmetry, and that is why x2 E2 should be a principal axis of the RB at point C. And the moment I realized that x2 E2 is a principal axis, I could conclude then and there that IC23, this one, and IC21, this one, this particular component must be 0. Okay, and once this is 0, and I know that inertia matrix is always symmetric, I conclude this is also 0. For the same reason, if this component is 0, this also has to be 0. Further, I realized that x1 E1 and x2 E2 plane is also a plane of symmetry, and that is why x3 E3 will also be a p-axis. And thus, IC23 and IC13 must also be 0. IC23 is already 0. We have already realized that. We have already put that as 0 on the matrix. The new information is that IC13 also should be 0. That's why I have that member as 0. And since this member is 0 here, this should also be 0, because the matrix has to be symmetric. And thus all off diagonal elements are 0 The diagonal elements I did find using performing full integration. Okay. So this we completed yesterday. Now I want to remind you why we are worrying about the inertia matrix after all. We have spent a lot of time on the inertia tensor and the inertia matrix. I did inform you about the motivation before I started this topic. But since it has been a long time, I want to remind you again that I am worrying about the inertia matrix because it helps me find angular momentum of the body of interest with respect to a frame. That frame is shown here. The body of interest is still cuboid, the same cuboid suppose. I would like to find very soon in this course the angular momentum of the cuboid about point C and with respect to F. And the way I am going to compute it is using the inertia matrix and the angular velocity. Indeed, it is a dot product between the inertia tensor itself and the angular velocity. This is the way I am going to get this HCF. Now the equation that I have here is the general vector equation. I can get three scalar equations from this. Those three scalar equations will be the equations for the three scalar components of this HCF vector. If I choose to use the same Cartesian coordinate system as my working coordinate system, then in general HCF will be written as H1E1 plus H2E2 plus H3E3, where H1, H2 and H3 are the scalar components of HCF vector in that coordinate system. Similarly, the angular velocity vector would be expressed in general as omega 1 E1, omega 2 E2 and omega 3 E3. And now that I have found that IC is the diagonal matrix for this cuboid, I am going to put that information here and I should be able to get H1 in terms of IC11 and omega 1, H2 in terms of IC22 and omega 2, and H3 in terms of IC33 and omega 3. This is the reason why I worry about the inertia matrix. It helps me find the angular momentum of the body. Another thing I want to highlight using this slide, which is on display right now, the working coordinate system. What is meant by the working coordinate system? The working coordinate system is the coordinate system which we are using to express various vectors of interest. Various vectors like HCF, omega MF, and there may be other vectors also. I am choosing a Cartesian coordinate system as my working coordinate system, right? This is the Cartesian coordinate system. Mind you, this working coordinate system is not fixed to frame F. It is fixed to the RB itself. This is very different from whatever we have done so far in kinematics. Whenever I had a Cartesian coordinate system, I used to say it is a frame fixed coordinate system, right? Frame fixed coordinate system. F fixed coordinate system. Now the way this is evolving, this formulation is evolving, we have started using a coordinate system which is not fixed to the frame but rather fixed to the body, or at least it has its origin fixed to the body. Later today, in today's class, later I will explain the importance of having the coordinate system associated with the RB itself rather than the frame. We will come to that. So explanation will follow, but for the time being I would like you to pay attention to this change of strategy. Now, having found the inertia components of the RB at point C, let us put it to some use. On the previous slide, I showed you that I can find HCF using the inertia matrix at point C and then taking a dot product with angular velocity. Now suppose for some reason you are being asked to find HAF rather than HCF. What is A? A is a point fixed on the RB, and A is actually this vertex of the cuboid, one of the vertices of the cuboid, specifically the one that I have marked there. Okay, we are being asked to find the angular momentum of the RB about point A with respect to F. Also, I am choosing my working coordinate system as what I have written here. So the origin of this working coordinate system is A itself, and the axes are x1 even hat, x1 prime e hat, x2 prime e hat, and x3 prime e3 hat. x1 prime e1 hat, x2 prime e2 hat, and x3 prime e3 hat as shown on the figure. Now if this is my working coordinate system, the yellow colored coordinate system is my working coordinate system, then I expect HAF to be of this form without any further condition or restriction. Okay, it will have three scalar components which would be H1 prime E1, H1 prime, H2 prime, and H3 prime. These are the three scalar components. So if I am able to find H1 prime, H2 prime, and H3 prime, I should be in a position to say that I know HAF, right? Now, H1 prime, these three scalar components would be what? Based on whatever we have done so far, how can we find that? I'm going to use this matrix, compact matrix form. This will be equal to something, some inertia matrix, and then you will have omega 1, omega 2, and omega 3, right? Where again omega mf, I am saying that omega 1, omega 2, and omega 3 are the scalar components. Those are appearing here. What is this matrix? What is this matrix? This matrix should be IA. This matrix should be IA. Contrast this with what I had on the previous slide. Here I had HCF, talking about this equation. HCF is IC omega mf. Why? Because I am trying to find angular momentum about point C. That is why I get inertia matrix of the RB at point C. Here I am trying to find, maybe I first write the full vector form. and then come to the matrix form. So here I am trying to find HAF, and thus on the right hand side I should have IA dotted with omega mf, right? And if I have to make a sentence out of this symbol, or I have to describe this symbol using an English sentence, it will be inertia tensor of cuboid at point A, right? And this is of course the angular velocity of the body with respect to F. And now if I write the matrix form of this equation, this would be right. Again, I want you to compare what I am showing here on the right hand side of this slide and what I had here. Here I had IC11, IC22, IC33. Here I have IA11, IA12, IA13 and so on. So if I have to find omega mf, I need to find this first. How do we find this? Given that we have already found this matrix here, is there any way I can find this matrix? So I pose this problem. Given that IC matrix is known, how do we find IA matrix? We will use the parallel axis theorem. We can use the parallel axis theorem. Okay. Let us use the parallel axis theorem to get IA, the matrix IA. Now one coordinate system is already there. The yellow color coordinate system I have already shown here. Let us draw the other coordinate system which has its origin at C, and let me call that as x1. Let me call the axis as x1 e1, x2 e2 and x3 e3. So now I have two coordinate systems. This is my first coordinate system and the other one is this. These two coordinate systems have some things in common. Some things in common. What is common? The unit vectors, the basis unit vectors are common. Right? E1, E2 and E3. It's a common basis. We can also say that the basis unit vectors of the yellow coordinate system are indeed parallel to the basis unit vectors of the white coordinate system. Correspondingly parallel to basis unit vectors of white coordinate system. Also, one of the coordinate systems has its origin indeed at the center of mass of the cuboid. At the CM of the RB. Both these conditions are required for us to be able to use the parallel axis theorem. I will say call this as 1, call this as 2. So 1 and 2 mean can be applied. Okay. Also, we know the coordinates of C relative to the yellow coordinate system. I call that as XC1, XC2 and XC3 primes. So if you use the yellow coordinate system as your working coordinate system, what are the coordinates of point C? Recall, this I am calling as A, this edge I am calling as B, and this I am calling as C. Where does C lie measured from the yellow coordinate system? Where does C lie? C lies at, according to me, it lies at this is where it lies. Minus A by 2, minus B by 2 and plus C by 2. That's where it lies. We have enough information to find IA11 as IC11 plus M XC2 square XC3 square. Right? This is the parallel axis theorem for moments of inertia. IA11 equals IC11 total mass of the RB multiplied by the square of the two coordinates, the second and the third coordinates of the center of mass relative to the yellow coordinate system. What will this be? Do we know IC11? Indeed, we have found IC11. In last class itself, we found IC11. It is here. M by 12 B square plus C square. So this is M by 12 B square plus C square. Total mass XC2 square is here. And XC3 is here. X prime C2 is here. X prime C3 is here. what do we get? So this will become b square by 4. This will be added to this 3 plus 4. It will become m by 3 b square plus c square. IA11. Right? So going back, I want to know each one of these members to be able to get the angular momentum of the RB. I have started working on it. IA11 I have found. You go to IA12. How do you get IA12? IA12 using the parallel axis theorem for the products of inertia equals IC12, right, minus m times x prime C1 x prime C2. That's the parallel axis theorem for us. What is IC12? Let's go back. IC12, which I found yesterday, 0. IC12 is 0. That will not contribute anything to IA12. How about this? M. What are the coordinates of the center of mass of the body relative to the yellow coordinate system? I will pick up this, I will pick up this. I need 1 and 2 coordinates of the center of mass. It's minus a by 2 minus b by 2. Okay, that turns out to be minus m a b by 4. That is IA12. Right? Now I leave this as a homework. You find the other components using the parallel axis theorem. Theorem. You should get this answer. I am giving the final answer for you to verify. This I have already found for you. This also I have just found, MAB by 4. Now, since it is a symmetric matrix, this will also be minus MAB by 4. The third one here turns out to be MAC by 4. This will also become MAC by 4. What does this become? This becomes C square plus A square M by 3. This becomes MBC by 4 according to my notes that I am having here. I leave it for you to verify. I might have made a mistake, so don't take it for granted. Do your own verification. It's not my responsibility, because I am not expecting you to look at it and memorize and use it. I am expecting you to follow the procedure, learn the procedure, how we are getting this. And once you learn it, you should be able to verify whether my answers are correct or not. Scrutinize, rather, I would say. Scrutinize whatever I write here. Okay. So this is the IA matrix. inertia matrix of cuboid, same cuboid but about point A and relative to coordinate system what I marked earlier as the yellow coordinate system. Okay, and thus we are now in a position to find the three scalar components of the angular momentum of the body about point A with respect to frame F. We will use these components. Right? So this is the procedure of finding HAF instead of HCF. The inertia matrix of RBs of common shapes about their own centers of mass is often available in tabular form in various books and texts. In your exam also, I would give you the inertia matrix about of an RB about its own center of mass. I will give you this matrix, IC. But I may ask you to find angular momentum of the RB about some other point. You should be in a position to use these inertia components here and then find angular momentum about another point like A, what I showed. Now let's look at a thin disk, and the quest is the same here. I want to find the inertia matrix of this thin disk at its center of mass, which is C, and relative to a coordinate system which I have shown here. So the disk is thin in the direction perpendicular to the screen, and indeed the direction perpendicular to the screen is the direction of E3. The entire disk lies in the plane of x1, E1 and x2, E2. Okay. Now I have to find all these 9 members here. This is the assignment. This is what I am expected to do. I will have to do some integration, no doubt about it. But for how many components do I need to do integration? Do I have to do integration for all 9 components? Or even before starting to integrate anything, I should first try to examine if any of these 3 axes of the coordinate system are the principal axis. If I know 1, 2 or all 3 of the axes are the principal axis, then I can set some of these off diagonal components to be 0 up front, and then I have to focus only on finding the diagonal components, right? So we recognize that in this case this body is a body of revolution. It has numerous symmetric planes, numerous planes of symmetry, right? it has a plane of symmetry which is x3 et e3 x2 e2 is a plane of symmetry, right? x3 e3 x2 e2 is a plane of symmetry, which implies what? Which implies that IC rather, I'm talking about IC1 3 and IC1 2 will be 0. x1 e1 is a p-axis. I also recognize that x1 e1 and x3 e3 is also a plane of symmetry, and this is all coming from visual inspection, VI. This is also VI. Visual inspection is telling me these things. x1 e1, x3 e3 is also a plane of symmetry. Right? It implies that x2 e2 is a p-axis. Which also means that IC12 is 0 and IC23 is also 0. So between this and this, we are in a position to say all off diagonal components 0. You don't have to do any integration. You can just cancel these out. 1 3 1 2 and 2 3. All 0. We are left with 3 potentially non-zero components which are lying on the diagonal of this matrix. But then we should realize that IC11 and IC22 are going to be the same. Disk is a body of revolution. And thus IC11, which will be what? x2 square plus x3 square dm, and IC22, which will be x3 square x1 square dm, will be identical. This is actually true for any body of revolution. Any body of revolution, these things will be true. There is really no distinction, nothing special about x1 e1 axis and x2 e2 axis. The distribution of mass on the body is identical. I mean, it makes no difference to the distribution of the body if you reorient x1 to x2 and x2 to x1. Doesn't matter. And that is why I need to do integration only for IC11 and IC33, because IC22 will be the same as IC11. Okay. But then this disk is also thin. Right? I am telling you, it is a thin disk. If it is a thin disk, then the parallel access theorem will be applicable here, right? For the disk being thin, it implies, sorry, not parallel access, but I mean perpendicular access. Perpendicular access theorem will be applicable. So if you go back to the previous lecture and look at the perpendicular access theorem, what did we find? What did we prove? What is the theorem about? That theorem tells us that IC33 is simply IC11 plus IC22, right? And I have already concluded that IC11 and IC22 are the same. Which means that IC11 will be IC33 by 2 that also exists. I mean, this relationship also exists. So the diagonal elements, the diagonal members of this matrix are not completely independent of each other, right? First we concluded that IC22 is equal to IC11, and now we are concluding that IC11 itself is IC33 by 2. What does it mean? It means after all I have to perform only one integration. IC33. If I can find IC33, other diagonal elements can be found very easily without integration. Let's try to find IC33. This is the disk. This is C. This I took as X1E1, X2E2. I'm going to take a small ring, a thin ring on the disk at radius small r, and mind you, r, big R is the radius of the disk. I marked it on the previous slide, I think. I consider a thin ring here. Okay. I write DIC33. I define this as contribution to IC33 due to the thin ring. Okay. You can see the whole disk as a composite body comprised of numerous thin rings like the one I have marked on the screen. And I am saying that DIC33 is the contribution to IC33 coming from this thin disk alone, a thin ring alone. So I'm saying that IC33 will be the integral of DIC33 over the whole disk, right? Such thin rings will keep contributing, and once you add all the contributions, it will eventually give you IC33. What is DIC33? What is DIC33? I would say DIC33 is dm times x1 square plus x2 square, which is equal to small r square dm. Small r marked here, radius of the disk. Further, I'm going to write dm as density of the disk material multiplied by 2 pi r dr. What is dr? Dr is this thickness. Dr is the thickness of this disk, multiplied by, say, T. T is what? T is the thickness of the disk itself. Pi r dr T. This is thickness of the disk in E3 direction. And this dr, there are two thicknesses involved here. This dr is thickness of the ring in the plane of x1 e1, x2 e2. I hope that clarifies. And rho is the density. So 2 pi r dr gives me area multiplied by this thickness of the disk gives me the volume of this ring, multiplied by rho gives me the mass of the ring. Alright, so DIC33 coming from here is what? It becomes r square rho 2 pi r T dr. Rho 2 rho pi T r cube dr. This is DIC33. Right? Are we ready to do the integration? I think it should be quite straightforward from here. DIC33 is 2 pi 2 rho pi T rho pi T r cube, right? So IC33 is integration of DIC33 over the disk, and that would be where r varies from 0 to big R. Look back, if you look at this figure, as I allow the small r to take value from 0 to big R, I will sweep across the entire disk. That's what we get here. It becomes 2 pi root t. But then I realized that pi r square t times rho must be the mass of the disk, right? Pi r square is the full area of the disk, t is the thickness, rho is the density, you get total mass. Okay. So eventually what happens is, and this 2 will anyway cancel out here, you get mr square by 2 IC33, and thus IC11, which we already know equals IC22, is mr square by 2 by 2, mr square by 2. So for that thin disk, the full inertia matrix is just include this figure for reference. Mass. Another result worthy of being put in a reference book, in a reference table. Once we have done the integration, we know what the matrix is. Keep it handy whenever you need to use it to solve a problem. Alright. Okay, we take a break. We meet at 5:10.